Okay, so welcome to lecture 11 of the series in Introductory Several Variable Calculus. Till now we have studied two very important theorems, which are the inverse function theorem and the implicit function theorem, and we have rigorously studied the derivatives, the existence of derivatives, what are directional derivatives, what are partial derivatives. And we had a definition in some previous lecture where we say that a function which is differentiable at some point is said to be continuously differentiable at that point if its partial derivatives are they exist and are continuous. Okay, in this lecture we will keep the functions a bit simple. Our main analysis will be on functions which are real valued, and we're taking two variables, that is functions from R2 to R, which are what we're going to discuss in this lecture. Fine. Now suppose you have a function. Suppose f is a function from let's say an open set E in Rn to R, let's say, and this set is open. Fine. With all its partial derivatives existing, with all partial derivatives existing. Okay, now if they are continuous, as we say that these are continuously differentiable functions, then we say, so this is symbol, just a sort of notation, then we say that f is a C1 function on E if f is continuously differentiable, that is each of the partial derivatives are continuous. Okay, furthermore these partial derivatives are also functions from Rn to R, right? So furthermore, if each del f by del xj exist on E, let me be a bit specific, let me say that it's just on E, exist on E and are differentiable, so I am already, since we are talking about differentiability, so I am already assuming that they are continuous. Fine. That is that we are talking about a C1 function on E, and are differentiable, then we can talk about these things, del x I by del x j of f. Fine. And these are sometimes simply referred to as del 2f by del x I del x j. So this is just, so we choose the partial derivative with respect to j coordinate, and if it is differentiable at some specific point we are concerned about, then we can also further partially differentiate it with respect to some the ith coordinate, and this is what we call a mixed partial derivative. This is typically what we call the mixed partial derivative. The mixed partial derivative. Fine. Now furthermore, if these are continuous, so so if these are continuous, that is, so what we have, so we have a C1 function with its second partial derivatives existing and continuous, then with keeping the analogy with how we are talking about continuously differentiable functions, these functions are called twice continuously differentiable, and we say, or rather we write f being in C double prime, that's the usual notation of E, that is C is twice continuously differentiable on. Fine. So we will rather use these symbols to denote when a function is continuously differentiable or when the function is twice continuously differentiable. Now the question is that if you see that it sort of intuitively seems that if I consider this del 2f over del xi del xj at some random point, so I am not specifying the point every time, so you can just think of it on E, or rather you can imagine it to be being talked about at some specific point, but whether this equals this. Okay, yeah. So what is the literary difference between them? So in this case what we are doing, we are first taking the partial derivative with respect to the jth coordinate, and then we are taking the partial derivative with respect to the ith coordinate. And in this case we are first taking the partial derivative with respect to the ith coordinate and then taking the partial derivative with respect to the jth coordinate. Now it sort of intuitively seems that these are, you know, looking to be sort of symmetric, and may be true, or rather if you are highly intuitive it should be true. That's something you might think of, but the thing is that that's not always the case. Okay, to see this you can just evaluate it out, because you already know how to calculate partial derivatives, and since we are talking about real valued functions, so rather let me talk about this. So suppose you know, f is a function from R2 to R defined as, let's say, xy x square minus y square by x square plus y square whenever xy is non-zero, and it's just 0 if xy is 0. So it's a function from R2 to R. Fine. Then you can easily observe, so you can easily observe, or rather you can choose it as an exercise, that the function f, its partial derivative with respect to x and its partial derivative with respect to y are continuous on R or R2. Fine. In fact, the del 2f over del x del y and del 2f over del y del x both exist. Just keep calculating. Both exist on R2 and are not continuous at, I guess, the origin. Fine. And you can easily evaluate furthermore, can easily evaluate that the derivative with respect to x and y, first with respect to y, then with respect to x, at origin this should be 1, and evaluating with respect to x first then y at the origin this should be -1. These might be interchanged, I don't exactly recall the values, but you can just check. One of them should be 1, one of them should be -1. That is the exact case. Fine. So you can just check this out, and what this typically means that it is not, in general they are equal, right? But there is also something very important to observe, that we have specified, or rather we want you to observe this, that the partial derivatives are not continuous at the origin, and exactly at the origin we find that these mixed partial derivatives are not equal. So there must be something concerned about the continuity of the mixed partial derivatives, and that's exactly the Clairaut's theorem. We are specifically talking about the Clairaut's theorem in case of a real valued function taking two variables. Fine. Okay. Because that's, I think that's more easy to talk about, more easily understandable, and rather more easily applicable as well. To prove the Clairaut's theorem, we need an an analogous mean value theorem, as we have studied in the in the single variable case, an analogous mean value theorem. So let us state this first. Okay. So theorem, we are whenever we are studying these theorems in this lecture, we are always assuming a real valued function is defined on R2. Okay. So suppose f is defined on E in R2, where E is open, and del f by del x, del f by del y del x, these two exist at every point. Fine. Suppose Q is a rectangle, okay, a rectangular region, such that its sides are parallel to the axis with AB and A plus H B plus K with H non-zero, K non-zero be opposite vertices. So we are talking about a rectangle of this sort, for example, of this sort, where suppose this is AB, then this is A plus HB, then this is A plus H B plus K, and then this is A B plus K. Fine. Okay, so these are opposite vertices. We are talking about a rectangle of this. You can easily observe immediately that the area of Q is just HK. Fine. Yeah, let's come back to the theorem. So we have this, then let delta FQ be this. So we take the deviation with respect to both the coordinates minus the deviation with respect to the first coordinate, keeping the second coordinate same, minus the deviation with respect to the second coordinate with respect to the first coordinate being same, plus f at AB. Fine. What we claim is that then there exists a point xy in the interior of Q such that delta FQ is equals to HK times del 2f by del y del x at xy. Okay, so this is our claim, and this is some sort of a mean value theorem. You can kind of relate it with the mean value theorem. Okay, because what are we concerned about is that we are given a region and we are getting hold of a point within the region such that this difference equation is sort of defined with some value within the region, things like that, because everything in this difference equation is concerned about the boundary, right? All these points chosen here are concerned about the boundary. Fine. The proof of this is quite simple because we have chosen real valued functions on R2. Proof: just apply the mean value theorem to each of the coordinates. Okay. Proof: let ut be f of t b plus k minus f of tb. Okay, then you can immediately observe that our definition of delta FQ is nothing but u of a plus h minus u of a. Fine. Now applying the one variable mean value theorem with respect to the x coordinate, with respect to the each coordinate on which f is acting, because f is defined on R2, right? We have some x between a and a plus h, some y between b and b plus k, such that delta FQ, which is u at a plus h minus u at a, this can be written as, using the mean value theorem, h times, that is the difference between the coordinates, times the derivative of x. But the derivative evaluated in terms of the partial derivatives, keeping in mind how we formulate u, is nothing but h, the first derivative x b plus k minus del f by del x xp. Fine. Okay, there is some redundancy or fallacy, I should say, using the term fallacy with respect to writing here x as well, here x as well. But as in the previous lecture, whenever we are trying to do write the symbol for the partial derivatives, then del x or del x1, it actually refers to the differentiating with respect to the first coordinate, whatever the coordinate be, and del f by del xi refers to immediately the differentiation with respect to the ith coordinate. Here, since we are talking about two variable functions, we are keeping x1 to be x and x2 to be y, okay, irrespective of the coordinates. So here we have 2x, but you just need to keep in mind that this del x refers to the first coordinate with respect to which we are differentiating, and this x is the coordinate which we are working with, okay, fine. Right, but then you can easily observe, then again reapplying the mean value theorem, because we have also got a y between b and b plus k. So then what I can do is, typically this is also a difference equation, so this should be h times b plus k minus b, which is k, times the second derivative, but this times with respect to y, because here we are concerned about the second coordinate. So this should be del 2f by del y del x at xy, fine. Yeah. So this is what we require to prove, fine. So this is basically sort of the mean value theorem with respect to two variables of a real valued function. Now we come to the Clairaut's theorem. I think it's called the Clairaut's theorem. I don't exactly remember, but I think that this was the name assigned to it. Suppose f is defined on an open set E in R2, and let del f by del x, del f by del 2f by del y del x, and del f by del y exist on E. And furthermore, this is the concerning point, that del 2f by del y del x is continuous at some point AB in E, fine, fine. So this is the case which we saw in the example, that the point where the mixed partial derivative was not continuous, there we had a difference between changing the order of differentiation. So we are keeping here that this is continuous at some point AB, then del 2f by del x del y exist at AB, and furthermore del 2f by del x del y is exactly equal to del 2f by del y del x at the point AB, fine, fine. Okay. So what is an immediate corollary? So we have chosen here that the mixed partial derivatives are continuous at some point in E. So what if the mixed partial, or rather what is f, what if f is continuously differentiable on E, twice continuously differentiable on E, then on the whole of E the mixed partial derivative should be same irrespective of changing the order. So let me first write the corollary that del 2f by del x del y is equals to del 2f by del y del x on E if f is a twice continuously differentiable function on F. So therefore for the mixed partial derivatives to be same, they need to be continuous. That is what we require to observe in this lecture. So let us quickly give a proof of the theorem. The proof is quite simple. Let A be del 2f by del y del x at AB, fine. We need to show that this exactly equals the the second partial derivative with the order being del y first and then del x at AB, okay. Choose epsilon greater than 0 and let Q be the same region as in the previous theorem. Fine. Then by continuity of A at AB, then for sufficiently small hk, we have by continuity that A minus del 2f by del y del x at xy is less than epsilon. Fine. Okay. But then from the mean value theorem, this del 2f by del y del x at xy, this is nothing but delta fq divided by hk from the previous theorem. So this implies delta fq divided by hk minus a is less than epsilon. So fix hh and let k goes to 0. But once we set k go to 0, this becomes actually the, so we can separate delta fq by hk into the second derivative and the first derivative from exactly the definition of partial derivatives. So this implies that del f by del y at a plus hb minus del f by del y at ab divided by h minus a, this is less than epsilon, right, by the definition of the derivative with respect to the second coordinate. Fine. But epsilon was arbitrary, right? Since epsilon was arbitrary, and we can easily see that above is actually the definition. If you just rigorously write the definition, then this is just the definition of the derivative of the second derivative taken with respect to x of the derivative at with respect to y at the point AB, nothing else. Okay, this is h. This is h. Fine. Which implies that del 2f by del x del y. So this is basically at AB. This must be equals to a. So it exists and it equals a. Fine. For sufficiently small h. So just sending h to 0 for sufficiently small h not equal to 0. Fine. And that's the end of the proof. Right. So what we get hold of is that once we have a function defined on an open set in R2 such that its partial derivatives exists, are continuous, and we have del 2f by del y del x, it also exists and it's continuous as well at some point AB, then then we can just interchange the order of the derivative that will exist and will also equal the other mixed partial derivative. Fine. So therefore, whenever you are concerned about two mixed partial derivatives to be same with respect to two coordinates, you need to check whether they are continuous or not, and whether one of them is continuous at the point you are talking about or not. And that's the end of this lecture. So in the next lecture, I'm thinking of what to bring up in the next lecture, but obviously I'll try to bring up something very interesting. So meet you guys in the next lecture.